Okay. So, today we will take up the finite dimensional norm space and subspaces. Okay. We have seen so many examples of the norm space like Rn, Cn, then L0, L infinity, Lp and so on and so forth. Some of them are of finite dimensional like Rn and Cn, while the others are infinite dimensional. So, we will first take up the case when the dimension of the norm space is finite, and we will see that in what respect this finite dimensional norm space is simpler than the infinite dimensional case. In fact, there are many branches where we use the finite dimensional norm space only, just like a approximation theory, spectral theory and so on. So, there we require the finite dimensional case. Now, in order to develop the results or to useful results for a finite dimensional case, we require a lemma which is the backbone for this total study, and that lemma is as follows. The lemma says that let x 1, x 2, x n, x 1, x 2, x n be a set of linearly independent vectors in a norm space x of any dimension okay. Then there exists a number c, a real number c greater than 0 such that for every choice of scalars alpha 1, alpha 2, alpha n, we have norm of alpha 1 x 1 plus alpha 2 x 2 plus alpha n x n is greater than equal to c times mod alpha 1 plus mod alpha 2 plus mod alpha n. Okay. So, this lemma, what is the meaning of this lemma? What does it tells to us? X 1, x 2, x n are given to be linearly independent vectors, and what we are taking is the length of the vector which is the linear combination of x 1, x 2, x n. So, what this lemma says that in case of a linearly independent vectors, one cannot find a linear combination of vectors x 1, x 2, x n involving large number of scalars alpha i's, but with a minimum length, minimum small vector, because it will always be greater than equal to c times sum of these scalars. So, you cannot expect that a large number of scalars are involved using these linear combinations of the vectors, but the length of the vector cannot be so small, it will always be greater than equal to certain number c greater than 0. Okay. So, that is the consequence of this lemma. The proof of the lemma goes like this. Okay. Let us suppose S is alpha 1 mod alpha 2 plus mod alpha n. Okay. Now, if S is 0, it means all alphas are zeros, all alpha i's are 0. Okay. So, once all alphas are 0, then obviously for any number of c, so for any number c greater than 0, this inequality 1 holds, is it not, for any c. because left hand side is also 0, right hand side is also 0. So, whatever the C you put it greater than 0, it is true. So, there is nothing to prove, and or some of these are S is 0, means all alphas are 0. But second case, if this is case 1, if S is not equal to 0, so if we can divide the equation 1 by S, each term by S. So, from equation 1, yeah. So, if S is not equal to 0, then let us divide the each term by S. So, from 1 we get alpha 1 x 1 plus alpha 2 x 2 plus alpha n x n divided by S. Norm of this is greater than equal to, say, mod of C. Is it not greater than equal to C? Or you can say like this, that norm of beta 1 x 1 beta 2 x 2 plus beta n x n is greater than equal to C, where sigma of beta I is equal to 1 to, because what is the mod of beta I? Beta 1 is alpha 1 by S, beta 2 is alpha by S, and beta n is alpha n by S. Okay. So, if we take the mod of beta I is 1 to n, this 1. So, it is required to prove is the existence of C which satisfies the equation 2. The equal to prove is existence of a number C greater than 0 such that 2 holds. Okay. So, finally, we are landing to the proof of equation 2 for such. Okay. Now, suppose this is not true. Suppose this is not true. Suppose it does not hold, of course. It means that there must be some sequence of beta 1, beta 2, beta n, for which sigma of this is 1, but the length of this is not greater than equal to C or greater than equal to 0, is it not? So, it means there exists a sequence say by n of vectors where the y m is beta 1 m x 1, beta 2 m x 2, beta n m x n, where the sigma of beta I m I is 1 to n is equal to 1. So, suppose it does not hold, means for any set of scalars we are claiming that this C must hold good. Okay. There should exist some C for which the equation 2 is true. Suppose this is not true, it means there is just a sequence by m of vectors where y m can be represented in this form, sigma of beta I is such that norm of by m this must go to 0 as m tends to infinity. Okay. So, in case if the 2 does not hold good, then we can find a sequence where norm of by n tends to 0. Okay. Now, for the fixed J, this sequence m is not power, it is basically shows the corresponding to by m we are using the scalar index. If suppose by 3 then b 1 b 3 beta 2 3 beta like that. So, it is not a power, it is an index, you can just put it within bracket also if you have some confusion, okay, like this. So, suppose this is bracket. Okay. Now, since the sigma of beta I m is 1, it means beta I m for fixed j or fixed I, this sequence beta j m, this sequence mod of this is less than equal to 1 for each fixed j, because of this result, because sigma of this thing is 1. So, this one is less than equal to 1. Okay. So, it means for fixed j, the sequence beta j m is a bounded sequence, is it not? This is a bounded sequence of scalars. And we know by Bolzano-Weierstrass result that every bounded sequence has a convergence subsequence. So, by Bolzano-Weierstrass theorem, So, by Bolzano-Weierstrass Bolzano-Weierstrass theorem, the sequence beta j m has a subsequence, has a convergent subsequence. Has a convergent subsequence. Okay. So, this for fixed j it has a convergence. So, for each j it is true, hence beta 1 m, and suppose beta 1 m has a convergent subsequence which tends to beta 1 as m tends to infinity. Okay. Beta 1 m has a convergent subsequence. Therefore, the by m which is equal to beta 1 m E 1, beta 2 m E 2, beta n m E n, this sequence will have a subsequence by 1 m which is say this subsequence, say suppose gamma 1 m E 1, and then this is beta 2 m E 2, beta n m E n, because this is a bounded sequence beta 1 m. So, it has a convergent subsequence say gamma 1 m, where the gamma 1 m this goes to gamma 1 m will tends to beta 1 as m tends to infinity. Is it okay now? By Bolzano-Weierstrass property or Weierstrass theorem, if a sequence is a bounded sequence of real numbers, then it has a convergent subsequence converging to certain point. So, this by beta 1 m has a subsequence say gamma 1 m which goes to beta 1 as m goes to infinity. Clear? Hence, we have a sequence by 1 m which is a subsequence. So, by 1 m has a subsequence say by 1 m which has this representation. Continue this. Now, again by 1 m, because it has a beta 2 m. So, beta 2 m has a subsequence say gamma 2 m, which goes to beta 2, as n tends to infinity. So, correspondingly we have gamma by 2 m as again a subsequence, and continue this up to say n step. Then we have a subsequence by n m, which is equal to say by n 1, by n 2, by n like this, okay, of by n of say by m, whose terms are of the form by n m is equal to sigma I is 1 to n gamma I m x I, where the sigma of gamma I m I is 1 to n is 1 with scalars gamma I, is it not? So, this sequence by n m, it will be a subsequence of y m, where y n m is this, sigma of gamma I m is 1, and with scalars gamma I m satisfying the condition that gamma I m goes to beta I as m tends to infinity, Hence, basically we get that the sequence as m tends to infinity, the y n m tends to a point y, which is sigma beta I x I is 1 to n, and sigma of beta I is 1, mod of beta I is 1 to n is 1. Okay. So, what we have assumed is that there exists a sequence by n which does not follow the lemma's result. It means that sequence by n m goes to 0 as m tends to infinity. So, where the sigma of beta I m is 1. So, using the Bolzano, we can construct a subsequence, and the subsequence is coming like this, where it goes to y. Clear? Now, x 1, x 2, x n are linearly independent vectors. Sigma of beta I is 1. So, all the beta I cannot be 0. Clear? All beta I cannot be 0. This is linearly independent set. So, it means that linear combination of this vector y cannot be 0. So, since all beta I is not equal to 0, all beta I is not equal to 0, or since all beta I is not equal to 0, is not 0, all beta is not 0, and x I, x 1, x 2, x n is a linearly independent set of linearly independent vectors. Therefore, the vector y is not equal to 0 vector. Okay. Hence, the norm of y n m which tends to norm of y is not equal to 0, because norm is a continuous function. Continuous function. This I will show you. Okay. So, if this sequence goes to a corresponding norm, will go to norm of y. Now, since y cannot be 0 vector, so norm length cannot be a 0 length, it will be non-zero. Clear? So, norm of y n will be different from 0, but by our assumption, the sequence y m is such that norm of y n tends to 0 as m tends to infinity. It means all of its subsequence must go to 0. So, this implies all of its subsequences, that is by n m, must have this property, that norm of by n must go to 0, is it not? Otherwise, it will contradiction the limit property. So, here we are getting this goes to 0, here we are getting this does not go to 0 as m tends to infinity. So, this itself shows a contradiction, and contradiction is because of our wrong assumption that we are able to get a sequence by n which have norm of which goes to 0, okay, where y m is the linear combination of vectors involving large number of scalars, but the length of this is a minimum vector. So, that assumption is wrong. It means we cannot obtain a vector involving the large scalars and a minimum length 0. Okay. So, this proves the result. Is it clear? Now, this result lemma has a wide application in establishing so many results in case of finite dimensional space. One can establish beautifully by using this lemma the results which are very important in case of the finite dimension. So, the first result which we add is in the form of theorem: every finite dimensional subspace capital Y of a norm space X is complete. That is, in particular you can say every finite dimensional norm space is complete. Is complete. Okay. So, if the space is finite dimensional, then by this result you need not to prove the completeness, because every finite dimensional space is complete by this result. So, R n is a finite dimensional, is a complete space, R 1 is complete, C is complete, R n is complete, C n is complete. Any finite dimensional if it picked up, it will be a complete norm space. Okay. So, in order to prove the completeness, what we will prove is that every Cauchy sequence in this, if it is convergent, then we say the space is complete. Okay. So, let us see the proof. First, we have assumed the subspace Y is of finite dimensional. So, assume let the dimension of Y is suppose n, okay, and let E1 E2 En, these are the basis elements basis for Y. Okay. So, any element of Y can be expressed in terms of the linear combination of the basis element. Okay. Now, we want this Y to be complete. So, let us choose an arbitrary Cauchy sequence. So, let Y n m is an arbitrary Cauchy sequence in Y. Let it be in arbitrary Cauchy sequence. Since y m is a point in Y and Y has a basis E1 E2 n, so y m can be expressed as, so y m can be expressed as a linear combination of the elements of basis. So, alpha 1 E 1, alpha 1 m because it corresponding to y m, alpha 2 m E 2 plus alpha n m E n. So, for each y m we have a unique representation for this. Okay. Now, since the y m is a Cauchy sequence, so apply the condition of Cauchy sequence. So, for since y n is a Cauchy sequence, so y definition for given epsilon greater than 0, for given epsilon greater than 0, okay, there exists an n depending on epsilon such that for all m and r, or sorry, for all m r greater than n, we have norm of y m minus by r is less than epsilon for or less than epsilon. Is it not? If y m is a Cauchy sequence, then for a given epsilon there exists an n depending on epsilon such that for m and r greater than n we have this. It means that epsilon is greater than this, epsilon is greater than this. Now, write down this expression. So, y m corresponding to this expression, by r will correspond to alpha 1 r E 1, alpha 2 r E 2, alpha n r. So, when you subtract, you will get like this, alpha 1 m minus alpha 1 r E 1, and like this, and rest last term will be alpha n m minus alpha n r E n, like this. Is it not? This is our norm of this. Okay. Which is can be written as, so we get epsilon greater than equal to norm of y m minus y r, which is equal to norm of sigma alpha I m minus alpha I r E I is 1 to n, and this is greater than equal to c times mod sigma of mod alpha I m minus alpha I r by the lemma, because E1 E2 n is a linearly independent vectors and these are simply scalars. So, a linear combination, finite linear combination of these vectors is there. So, we can find a c. So, there exists a c greater than 0 such that this is true, okay, by lemma I is 1 to n. Therefore, from here we can say mod of alpha I m minus alpha I r is less than equal to epsilon by c for all m and r greater than n, okay, for fixed I. So, for fixed I we get this thing, is it not? Sigma is less than a. So, for each I you can get this one. What does it mean? It implies that for each I, for fixed I, the sequence of scalars alpha I m behaves as a Cauchy sequence. Cauchy sequence of real or complex numbers. Is it okay? Because this is the Cauchy definition of Cauchy. Difference between any two arbitrary term after a certain stage is less than epsilon. So, it is a Cauchy sequence, but real and complex number is complete. So, this Cauchy sequence must be convergent. So, alpha I m goes to alpha I as m tends to infinity, because this is a Cauchy sequence in real or complex is a convergent sequence. Therefore, for each I, this is true for each I, we get. So, what we get is now, so the sequence by m, which is alpha 1 m E 1, alpha 2 m E 2, alpha n m E n, this will go to the element by, which is of the form alpha 1 E 1, alpha 2 E 2, alpha n E n as m tends to infinity. Okay. Clear? Now, y is a linear combination of these basis element E 1, E 2, E n. So, is it not a point of the space? It belongs to y. So, obviously, this is an element of y. Clearly, y belongs to capital Y. Okay. Is it clear? Now, the question arises whether this convergence is in the norm of y or not, because if it is in the norm of y, then the every sequence has a convergence every Cauchy sequence converges in the norm of y. So, we have to show that this convergence is in the norm of y. So, let us take the norm of y m minus y. Okay. Now, this can be written as norm of sigma I is 1 to n alpha I m minus alpha I E I. Okay. Now, this will be less than equal to some constant times k sigma of norm alpha I m minus alpha I is 1 to n, where what is k? K is okay, where what is k? K is the maximum value of where k is the maximum value of the norm E I when I varies from 1 to n. Okay. So, we are taking where k is the maximum of norm E I is 1 to n. Okay. So, this is the maximum value of E I and replace it. Now, let us look this again. If we look this equation, say equation 3, as m tends to infinity, alpha I m is tending to alpha I because of this result, is it not? Because of this A already shown. So, this part is tending to 0, this is finite number and k is already finite. So, basically as m tends to infinity, by m go to y under the norm. So, as m tends to infinity, by m tends to y in the norm of y, okay, and this completes. So, y is complete. Okay. Is it clear? Now, this result is valid for in case of the finite dimensional. That is, if we take any finite dimensional subspace of a norm space, then it must be complete. Okay. But if it is not finite dimensional subspace, then it may or may not be complete. So, in case of the infinite dimensional subspace, in case of infinite dimensional subspace, the result is not true, result may not hold. may not hold. Okay. For example, if we take the space X as C01, set of all continuous function defined over the closed interval 0 to 1, and this is a complete under the metric norm of X as the maximum of mod xi, maximum of mod xi t or xt, maximum of mod xt, where the t ranges from 0 to 1 under this norm. Okay? It is a complete metric space. Clear? Now, I am choosing the y as the span of x naught, x 1, x 2 and so on, where x I t is equal to t to the power I. So, I am taking this y as the linear combination of the elements of 1 t, t square and so on. So, basically it is the span of 1 t, t square and so on. Clear? So, it means y is a polynomial, set of all polynomials, because when you are taking a linear combinations of this 1 t, t square etcetera, you have to pick up a finite number of the points only at a time, and once you take the finite number of points, the linear combination of this will give a polynomial. So, basically it is a polynomial. So, collection of the polynomial, and these polynomials are also continuous function. So, y is clearly the set of all polynomials हो जाएगा, is it not? This is the set of polynomials. Okay. Elements will be the polynomials in that. Now, this y is clearly y is a subset of C01, is it not? Because every polynomial is a continuous function, and C01 is the set of all continuous function defined over the closed interval 0 to 1. So, it is a subspace, subset or subspace of C01. Now, question is whether it is complete or not, because this is a infinite dimensional. The dimension of y is not finite, because it is a infinite dimensional. So, we claim that this will not be a complete space. Why? Suppose I take the sequence y n t as 1 plus t square by 2 plus t to the power n y factorial n. Okay? Suppose I take this sequence, it is the point in y. Okay. What is the limit point of this? As n tends to infinity, it go to the point by t, which is e to the power t, is it not? As n tends to infinity, it will go to as, because it is an expansion of e to the power t, basically 1 plus t square by factorial t n to the power etcetera, which is not a point in capital Y. Okay. Is it clear? So, it means this limit point of this is not a point in y. So, this y is not closed. So, y is not closed. So, y is not closed, and this already we have one result. A subspace of a metric space is complete if and only if it is closed. Similarly, a subspace of a norm space is Banach if and only if it is closed. So, if this is not closed, it means y cannot be a complete norm space. So, y cannot be complete. So, y cannot be complete. Clear? So, though it is a subspace of CAB, but it is not complete because the dimension is finite here. So, it in case of the infinite dimensional subspace, the result is not true, but finite dimensional it is always true. Whatever the x may be. If I picked up a finite dimensional space, it must be a complete space, okay, of any dimension. So, this is one of the. Now, another interesting application of this lemma is about the equivalent norms. The equivalent norms we have defined already. Let me revise a norm on a vector space, a norm on a vector space X is said to be equivalent to a norm 0 on X if they are all positive, numbers alpha and beta, such that for all x belonging to capital X, we have alpha times norm of x 0 is less than equal to norm of x which is less than equal to beta times norm x 0. Okay. Norm x 0. For example, let us take the examples here. Suppose I take.
So, how can it be?
Huh?
I mean, how can it be between these two?
Yeah, alpha and beta. Yeah, that's right. Means if there are two norms are there, okay, find out the value of x, any arbitrary x in one norm, and then find out the value of the same x in other norm. If this condition is verified, that is norm x will lie between this and this with a suitable alpha and beta, then we say both the norms are equivalent norm. Okay. For example, I am taking this example, just give it.
So, this is I mean in the center portion,
Ah.
x norm x, it is not norm x 0.
No, it is only norm x, no norm x 0. Okay. This is not, it is a no norm x 0, it is only. Suppose I take this example, say, okay, suppose x is equal to say R 2, okay, and I define and let x is x I 1 x I 2 be an element of R 2, okay, be an R 2. I am defining the norm x 1 or x 1 as mod x I 1 plus mod x I 2. The norm of x, another norm I am defining as under root mod x I 1 square mod x I 2 square, and continue this. Suppose I define norm of x p as under root mod x I 1 p mod x I 2 p and power 1 by p. This is power 1 by p, okay, power 1 by p. So, that is the meaning is mod x I 1 p plus mod x I 2 p power 1 by p, where the p is greater than 1, okay, and norm x infinity, say I am defining as maximum of mod x I 1 comma mod x I 2. Suppose on R 2 I am defining this, you can verify that this forms the norm.
So, p is greater than
1, p is greater than 1, okay, because we are starting 1, 2, 3 and so on. So, p must be greater than 1. Okay, for various p's you can find out this thing. Now, if I look this 1 and 2 now, x 1 and x norm x 1 and norm x 2, then what we get it from here is norm x 2, norm x 2, what is this is under root mod x I 1 square mod x I 2 square, is it not? Now, this will be written as sigma, okay, x I square I is 1 to 2 and power half, okay, clear, power half, let it be 1. Okay. What is the norm x 1? Norm x 1? The norm x 1 is mod x I 1 plus mod x I 2. Now, this is equal to sigma mod x I is 1 to n 1 to 2, okay, 1 to 2. Is it okay or not? Now, if I apply the Holder's inequality, keeping this as this is the point I is 1 to 2. Suppose x I and by I are the two terms, okay, and apply the Holder's inequality. Then what is this result says? Sigma of 1 square I is 1 to 2 power half, is it not? Then sigma of mod x I square I is 1 to 2 power half, is it not? By Holder's inequality or Cauchy-Schwarz inequality you can say, for p equal to 2 it is Cauchy-Schwarz inequality. So, we are saying this one, clear. Now, what is the sigma 1 square? 1 square is 1. So, it is basically 1 plus 1 is 2. So, basically this is coming to be root 2 into, is it not a norm of x 2? So, what we conclude that norm of x 1 is less than equal to norm of x 2. Is it okay? Clear? Huh? So, a constant beta can be obtained under 2. So, norm of x 1 is lying with is this one. Is it okay or not? So, we can say 1 upon root 2 norm of x 1 is less than equal to norm of x 2. Let it be this second, not this, let it be put it this form. Okay. Clear? Further, norm of x 2 as is given by this under root mod x I 1 square mod x I 2 square. Now, is it not less than equal to mod x I 1 plus mod x I 2? This is valid because if I square both side, then this square will be higher more than this value. So, this is valid always, but what is this? Is it not the norm of x 1? Okay. So, this is third. Combine 1 and 2, we get norm of x 2 is greater than equal to 1 by root 2 norm x 1 is less than equal to norm of x 1. It means, here the alpha is 1 upon root 2, beta is 1. So, we can find out the scalar alpha and beta, so that these two norms can be put it into this or can satisfy this inequality. So, both these norms are equivalent norm, clear. Similarly, we can go for any other norm. So, all the norm which we have defined in this fashion, they are all equivalent norm. Okay. Now, what is the advantage of the equivalent norm? Okay. if I define the here the sphere, say if I take this problem like the spheres unit sphere S01 with the center 0 and radius 1 is the set of
The matrix condition numbers,
huh,
they are defined with these norms.
huh.
Matrix condition numbers.
Matrix also, yes, is same.
Can we take such an example which can be of or help actually?
Which can be metric.
Yeah, I mean matrix.
Matrix.
I mean the
Oh.
condition number of a matrix.
Matrix also we can do it. Yeah,
Yeah. So
we can. Okay.
define the condition
Equivalent
number.
norms. All the matrix of the Rn matrix, they will all whatever the m cross n matrix are there, whatever the norm, I will give it example where the norms we can define in many ways, and this becomes a equivalent topology.
So you can define the condition number of a matrix
Huh?
based on these norms. So I mean one
Yes.
of these norms.
Huh?
So I mean, can we discuss this point? I mean,
Yes, we
an
can.
example.
Example only finite case. In finite dimension, we cannot say anything.
Yes, sir.
Only finite case it is true. Okay, that we come. Let us see this one. X belongs to capital X such that norm of x equal to say 1. This is the unit sphere in a norm space X. Now, if we look this previous results, then here we can say this one, that suppose we have this. Okay. This is the center here. So, basically the unit sphere yes, this is the unit sphere in case of norm x 1 equal to 1. Okay, because it is a mod x 1 this is the center 0 0. Okay. So, and then slowly it goes like this like this and something like this. So, it goes to the norm x 2 and this one basically finally norm of x infinity is 1. Okay. Now, when these norms are equivalent, the corresponding topologies are the same. So, in case of the equivalent norm, the corresponding topologies are same. They give the same topology. Okay. Topology means collection of the sets, that open sets. Okay. That is I did not define the topology earlier. In fact, the topology we will teach you later on when we go for the some other further, but this you can simply understand that we are getting the open sets. Okay. So, whenever you pick up any open set in one norm, correspondingly you can get another open set in the suitable open set in another norm. So, that one can take a sequence which converges in one open set, it will converge into the other open set of the other norm, like then vice versa. So, this way we can do. Okay, thanks.